Hello everyone, and welcome back to the channel. Today we're going to be doing another slideshow kind of video here. We're just going to be talking about the C language, giving a bit of an overview of the C language and some of the language features and explaining some of the syntax that is common in my videos and will continue to be common in my videos. This first video is focusing on beginner concepts that are, like I said, all over my videos. It's baseline information that you'll need to be able to follow along with the videos. I assume generally that the people who have watched the few videos on my channel so far have already had experience with C and already experience with programming languages in general. And it's true that a lot of people are getting to these videos and have seen some programming before, but C is actually not that common. At the university, it was the first language they taught us, and I only just graduated in 2021. So when you think of it, you know, it's not like I have outdated education. I started in 2017, and C was the first language they taught us, and I think that was a very good thing. It's a very, it's got its tricks, and it's sticky in just the right way, but it sets you up good to be able to understand other languages. So the topics that I've decided are going to be beginner topics, and some of these maybe are beginner intermediate, not quite beginner concepts, but it just feels like the bare minimum for me to be able to put in a video and say, yeah, we talked about C. It's almost everything you need to understand my demos. I really wanted to squeeze arrays in here and pointers, but then it would be a 3-year-long video, and I just don't know what the impressions are going to be like on that one. So the order of the topics we're going to cover here, we're going to talk about the language keywords, which is going to tell us what we can't use for identifiers. Then we're going to take a look at Hello World. I know if you're a programmer, I know we don't want to see Hello World anymore. You know, I'm sick of seeing it too, but it's something we got to do. The headers, so we're going to take a look at the standard library and its headers and talk a little bit about what that means. Then we're going to talk about function calls and how those work and sort of allude to the function call stack. And I will provide resources for a lot of these for extended reading. Then we're going to talk about variables and their scope, talk about control structures such as the if statements and the loops. And then lastly, we'll finish off with user-defined functions, how we can define our own functions and just some of the rules we need to keep in mind there. So the C language has a list of reserved keywords that are being used by the language, and they have their own predetermined functionality. So this is a list, I guess you could say. There may be more, but these are sort of the keywords according to cppreference.com. By the way, I just want to go ahead and cover this really quick. cppreference.com is a website that has a language reference for C++. But if you just scroll down, there's a C reference language. You can click right here, and you can go ahead and bookmark this. And this is a language reference for the C. So you have all the different standards here, C89 through C23. And you can see different language concepts here. You can read up on these. You can read about different types. You can see the list of headers. So this is where I got my keywords right here. And if we go back, we can see a list of headers that we'll see later. So CPP reference is our friend. We're going to see a lot of screenshots from that site today. It does have a C reference. I'll have a link down below if you don't want to go find it yourself. It's totally worth jumping over to that and reading if you're left with any huge questions from this video. And of course, please leave it in the comments if there's anything that you want me to clarify. So these are the keywords anyway, according to CPP reference, but honestly, most of these we're never going to use. So these are the keywords that we're actually going to use, the ones that are not blurred. There's one or two here that I've excluded that eventually you'll see here and there. But honestly, there's so many keywords that I didn't even know were in the language, and I've used C for years because it's just they're so niche, or they're in such a new standard that I don't generally use that standard, so I wouldn't even have access to them. And honestly, a lot of them I was like, I didn't know C had that keyword because it's something from C++, and then I read up on it, and it's like, oh, it does not do the same thing as C++ does. So these are the words we're actually going to get into. So the first set is the types. So these are something that we're going to use when we create variables. It's something that we use when we write a user-defined function. It's so that the compiler knows how much memory to allocate for something. So whether it's for the return value of something or a variable, different types occupy a different amount of space in memory. It also makes it so that in the IDE, if we try to assign a float to an integer or try to assign a string to a character, we can get a warning right off the bat that's like, oh, this doesn't go here. And if we make a small typo in our code and we put the wrong variable name or we put the wrong value, then it's an easy way to catch those kinds of things. Some languages don't have typed variables like this. Something like Python, you can put anything and anything, and it's really flexible, and JavaScript is similar like that too. And that has its practical uses, and it can make development easier in a lot of ways, but it can also make the language a lot more error prone, and it makes it difficult for an editor to say definitively this is an error because it doesn't know what your intention is. Where at least if you have a type, they know that you intend to put something of that type there, right? This is kind of the difference between drilling circular holes that are big enough to fit any peg or drilling the right-sized holes for a square, for a triangle, and so on. The types in C, at least in the order that they appear in this list, this might not be the order I would normally list them in, but we have a character, which is spelled C-H-A-R. Sometimes I'll say car or character. I will almost never say char. Then we have double, floats, ints, and void. So void is kind of a non-type. It's more commonly going to be used for user-defined functions to say, hey, this function's purpose isn't to return something, it's to do something. But it is also possible that void will work its way into a variable. It's also possible that void will work its way into a variable definition or declaration. And that's very much an advanced concept. It's related to pointers, and we'll get there when we get there. Not in this video. The other keywords that are not types but type qualifiers. So we have const, which is basically going to create a promise that we're not going to change the variable. It's not as simple as literally making it a const value, like something that can't be changed. There are certain cases where you're allowed to use it that way, and certain cases where you're not. If you're really interested, you can read the CPP reference page about it. It's quite the rabbit hole. Bring a pot of coffee, bring a flashlight. It's going to be a deep dive for sure. Generally speaking, it's safe to just kind of say, okay, this is a value that I'm never going to modify. But it's funny because if you take a const and you try to store the value of a const in a non-const, sometimes the compiler freaks out. So you may not end up using it after all. I try to use define instead, and there's a preprocessor directive for it, which I don't cover in this video. I didn't fit it in the content, but there's other ways to do a constant value. One thing's for sure, you don't want to just write the value in all the places it needs to go. You want to use const or you want to use define. You don't want to just write 10 everywhere and then nobody knows why you put 10. Next up, we have the short and long. So these are both qualifiers for an int. So a short means however much space an int takes, let's say it's 4, a short will only take 2, and a long will take 8. So short halves the space required for the variable, and the long doubles it. Now, by halving the amount of space an int takes or doubling it doesn't reduce the total possible value by half or double it. It's way more than that, and we'll see that on the next slide. But first, I want to talk quickly about signed and unsigned, which is also covered on the next slide. The gist of this is basically that for integer types like int, long, short, character, for these types, if we make it unsigned, the largest possible value becomes doubled because all of our negative values become possible positive values. And if we do signed, then that's kind of like the default. Like integers by default are signed. Characters sometimes are signed. That's one of those cases where it's implementation specific and you want to be careful. If you need a character to be signed or unsigned specifically, write it. It doesn't hurt to say signed int. Sometimes it's a good thing because it's specific, but int is generally going to be signed. So here's the table that talks a little more about the types and their sizes. So a character is always going to be 1 byte, which means we're either going to get -128 to 127 or 0 to 255. That depends on the signed or unsigned, as we see in the next 2 rows. On the 4th row, an integer could be 2 or 4 bytes. It depends on the system. And look at the difference it makes. 2 bytes is -32,000 to 32,000. 4 bytes is -2 billion to 2 billion. Right? Look at the difference. And if we make that int unsigned, it's 0 to 65K or 0 to 4.3 billion, right? So clearly making it signed or unsigned can make a huge difference. But if what you're really after is a big number, a big whole number, you're going to want to go all the way to unsigned long. That's 8 bytes, which is, I think that's like 20 digits, 19 or 20 digits. So if you really need a really big number, That's the one. You want to use unsigned long, or even long, because long is just one fewer digits than whatever unsigned long is, which, I mean, I don't even know if there's a name for a number that's 19 or 20 digits long. But I mean, when they say long, they're not kidding, right? So if you ever need to know exactly the size of a data type, or if you need to know the possible limits, there is header files for that, and we're going to get there in just a second. But moving on from the types, we're going to have the control statements. So the famous ones here are the for, do, and while. Those are the loops, right? You have your for loop, which even if you've never programmed before, you may have heard of. And then there's while and do while loops. That's probably the order that they're usually referred to, because that's the order they're used in. For is the most common, while is next common, do while is like virtually extinct. The keywords break and continue are related to loops as well. So we can use continue to skip to the next iteration of a loop, and ignore the rest of whatever's left in the loop body from the moment it's called. And break can be used to break out of the loop and say, we're done with the loop. So if the loop is supposed to go 20 times, but then we hit a special case early on, we can say, let's get out of here. Now, how do we only do the break in that special case? That's where the if statement comes in. So an if statement is that's your classic conditional code. The if statement is the beginning of branching programs. So when we have any kind of input coming in from the user, whether it's them typing in a word, it's them clicking on a button, it's the time on their computer, if anything can vary based on external factors in the program, we're going to want to use if statements to break out the program into multiple cases, code that's only going to happen under certain conditions. So during a loop, we can say, if we reach the special case, break. And it's going to break out of the if statement, out of the loop. Now, you can nest loops in loops. So if you break out of an inner loop, it's going to put you out to the outer loop. So it's not going to break all the way. So there's other stuff you got to do there for that. But that's the break keyword, the continue keyword. Break has another use. So there's another kind of conditional statement called a switch statement. And a switch statement is really made up of switch, break, case, and default. So those four terms together makes up a switch statement. And that's something that we're going to cover when we get to control structures. It's a very powerful control structure. I don't see it used a whole lot, but it can make some pretty neat looking code. To pair with the if statement, there is the else statement. They kind of come hand in hand, so I'm not going to dwell on that too much. And the only other keyword here is return. So return is the exit point of a function. It allows us to, if we have a void function, we don't really need return. It's used as like an early out for a void function. But for anything else, for int, float, for any other kind of functions that have a non-void return, we're going to need to have a return statement somewhere, or we're not going to compile. There's a few more keywords here. These ones are not going to be covered in this video at all, but it's worth mentioning. So we have enum, struct, union, and typedef. Those four kind of go hand in hand. So an enum is basically a named integer. Instead of saying this variable can be any integer, but we really only care if it's 0 through 4, we can create an enum that says the value 0 is called, it has a name. So let's say right, down, left, up, and we call that enum direction. Now we have a kind of integer that can only take on 4 values, which are right, down, left, up. And each of those word values correspond to some number. We don't need to worry about the number. It's not important because we always use the name. And this makes it easier so that if in your program you need to have this concept of a 4-directional direction, instead of remembering that 0 is right and 1 is down and 2 is left and 3 is up, we can use an enum to kind of obfuscate that concern, and we can deal with words, which would rather code in English than in numbers. A struct allows us to take multiple data types, multiple data pieces, and string them together. So I use it as kind of like an object. I've used it in every demo. It'll probably make a scene in every single demo because it's a useful way to combine. If you have 2 ints, a float, and an enum that all together defines an entity in the game, it's really helpful to just use a struct. Now, it's not really an object in the way object-oriented programming is, but it's certainly good enough for my little Raylib games. Union is going to be a optimization keyword that is really just used to deal with structs that get very large and have multiple values that may go unused. Union is a very complicated subject. It feels very advanced. It's something that the vast majority of my colleagues that studied the same computer science program as me never even saw because It's just such an end game feature. It's one of those things that really keeps C relevant in my eyes. It's a very cool keyword. And like I said, if we ever get to those really advanced videos, we can talk more about it. Type def is something that union, struct, and enum are all going to use to make the syntax a little bit neater. Size of can be used like a function. We can put parentheses after the name, and it basically just tells us how many bytes a data type uses. You can also put variables in there, but generally speaking, size of doesn't get a lot of use, but it's the kind of thing that if you are worried about integer limits and things like that, size of is one of the ways you could find out what's going to be safe. Lastly is a static keyword. Again, more of an advanced keyword. Basically what it's going to do is if you have multiple code files in your project, which we're not there, but if you do, it just means that whatever variable or function you write after the word static is going to be limited to that file. So it's a way of signaling to the programmer that it's an internal function or a private function to that file, and something that's basically a utility. And same thing goes for the variables. It's something that is a utility to that function or that file. I encourage you to go to CPP reference and read about these keywords and let it shatter your world, because you're going to realize I had no idea C could do all this stuff. So yeah, I do encourage you to go and read them, but just remember that you don't have to know all that stuff to be able to succeed in C. So the reason we started with keywords is so we can move into identifiers, because one of the rules of identifiers relies on the knowledge of keywords. So an identifier is the name of a variable or a function. We're going to see them all over the place, and there's actually, they're pretty straightforward. There's not a lot of rules. So identifiers, it's A to Z, big and small, 0 to 9, underscore. So the rules of what identifiers can't have, aside from things that aren't what I just said, they can't start with the number. So they can have numbers in it. You can have x1, x2, x3, but you can't have 1x, 2x, 3x. That's not allowed. An identifier can't contain white space. You can't have a space in the middle of your name. There's certain rules that say this is what an identifier is, and white space signals the end of an identifier. So you can't have a new line or a space in the middle of a variable or function name. And the third thing is an identifier can't be the name of a keyword. The name's already taken. So you can't make a function called switch. It's not allowed. I think you could do it with an uppercase S, but I think that's a terrible idea, because that's not going to be, easily identifiable. Now, the way you name your variables and your functions, as long as it suits these rules, it doesn't matter what the hell you call them, right? It just matters that you pick something that works for you and you use it across the board. Pick a convention you like and stick with it. Now I'm going to cover a couple of name conventions on the next slide. So the three most common naming conventions for identifiers are as follows. We have camel casing, snake casing, and Pascal casing. Now I'm sure from these examples on the right in bold, and I have some color coding there to really send it home, I'm sure you can kind of understand what they're going for here. So a camel case, the first word is always lowercase, and then every word after the first word inside the identifier, the first letter is capitalized, so that you can easily pick out where each word begins and ends. Snake casing, words are separated by an underscore. This one's probably the least common. And then we have Pascal casing, where each word starts with a capital. So it's camel casing without that special case of the first word. So these are the three most common conventions that I've seen for naming identifiers. And there's a lot of debate on which ones are the right ones, but it's like I said on the previous slide. Don't worry about what's objectively the right one. The objectively right thing is the thing that you're going to remember and that you're going to be able to stick to. But it should be project-wide whenever you choose something. So the correct choice isn't to choose one of these and use it for absolutely everything. It's to use one of these for each type of thing. So for me, for my own project, I personally like to use an uppercase snake casing for constant values, something like cell width, maybe it's 100 pixels. That's across the board. The whole project is using it. So I use uppercase snake casing to identify that it's a constant value. And at a glance, I can tell that's a constant value. Then I'm going to use camel casing for any variables. And lastly, Pascal casing is how I name my functions. And this is also how Raylib the functions are named. But like I said, it's all about using a mix of these, but you want to be consistent. So I have my own personal rules, and I use those in my videos. Now we're on to the hello world. So the hello world is, like I said, something that if you're a programmer, you're sick of seeing it, but it's a great example because it's a program, it's a full, complete program that does a single thing. You could take this, paste it into a compiler, it'll run. So this is one of the few code snippets I'll be showing today that is actually a full program that'll work. So it comes in 4 pieces here. So we have an include statement at the top, which is in gray. This is a type of preprocessor directive. It's going to basically import some code that has been part of the standard library. In particular, it's going to import some code that we need to be able to print something to the terminal. Then we have the main function definition, and those are really the two parts of the program, the include statement and the definition of the main function. Now, the main function is the entry point of a C program. So if you want to write a program in C that is executable, it needs to define a function called main. As I've already said, I'm like a broken record. Go check out the CPP reference page about the main function, and you'll see there's a few different ways you can write it. Again, pot of coffee and a flashlight. It's a rabbit hole. Inside of the main function definition, there's two parts. There is a printf function call. Printf stands for print formatted, so as in print formatted text. So we call that function, and we have a return statement. The two parts of a C function definition are the function signature and the function body. The function body is written as a block of code. A block is defined by a pair of opening and closing braces. When we talk later about variables and scope, we will learn that each block has its own scope. The return type of main in my case is int, which means when I use the return statement, I have to include an int. So the word int before main is the return type of the function, and we'll talk more about that with user-defined functions. And the return statement has a 0 after it, which that 0 and that text in quotations, those are called literals. So we have a string literal and an int literal. There's a literal for every data type in C, so there's float literals and such like this too. A string literal is just going to have quotation marks on either end, and we can just put any text in there. We can use special text, which are called escape characters, such as the \n, which is going to put a new line at the end of the string. This is just something we do in terminals so that doesn't like screw up the way the shell looks when we run the program. And then we have an int literal, which is me just writing a number. So a literal is you spelling out the value literally, as opposed to putting a variable or a function call there and letting those provide the value. Both main and printf are examples of functions, but they're two examples of different kinds of functions. So main is the instance of a function definition. We're defining what's going to happen when we call main. Whereas printf, we're just calling a function that is already defined. So printf is defined inside of that header that we are including at the top. And main is something that we are creating. Main is our function. And like I said, we need to create main if we want to be able to compile an executable C program. So this include statement, inside of those angled brackets, this is kind of like a parameter. So in this case, that is standard IO. It's from the C standard library. So from the CPP reference, I have a list of the C standard library header files. Just like with the keywords, most of these you're never going to use, or it's going to take a very long time for you to get to the point where you're using them, or there is an alternative that Raylib is providing that we don't really need it, or you're using a third-party header. I mean, a lot of these we're just not really going to use, but they are being used by the libraries that we are including ourselves, such as Raylib or Raymath or whatever else. So this was from the CPP reference site. Like I said, you could see their headers is one of them. And there's actually one that's kind of missing from this list. It's called Standard Library, which is the name of the whole library, but it's program utilities there. It's if I click here, there's a standard IO in blue, and then right below it is program utilities, and that is memory management, program utilities, string conversions, random numbers, algorithms. It's just a bunch of general utilities from the standard library. It's one of those actually important headers that we're going to use. It's just not listed properly in this page, which is fine because it's probably improper that I call it the standard library when in reality it's the utility header of the standard library. So anyway, most of these we're never going to use. Like I said, don't worry so much about it, but it's not a bad idea to, if you've got that pot of coffee and you've got that flashlight from earlier, take a deep dive and just take a peek at all these and see what they do. Now that we've talked about headers, we're going to talk more about what happens when we actually call a function. So this is an example of a program which has a user-defined function in it. It's going to take in a number, it's going to add 1 to that number and print the number plus 1. We'll get more into user-defined functions later and more what that really means, but this is just a good example to show the flow of what happens when we actually call the function. So when we start the program, we start at this line. We start from main, that's the entry point to an executable C program. And the first thing we're doing is calling function 1. So we're going to store off where we are in main in the function call stack, and we're going to jump to the definition of function 1, like this. So the red is where we were, but now we're in fun1, we're on that printf. We're going to execute the printf procedure as we need to, and then we're going to jump back to main. We've finished fun1. We're going to move on to return 0, and the program is done, because if you return from main, that ends the program. So the reason I cover this is because the idea is that when we call a function, we're basically pausing the function we're in now, we're going to that function, and when that's done, we're going to resume where we are now. So now we're moving on to variables. So variables are a method of storing a value which is allowed to vary throughout the lifetime of the program. This is basically one of the most important things that we're going to have in programming, especially when it comes to game design. We're talking about user input. So we write a type followed by the identifier and a semicolon, and we can declare a variable. So here's a float called percentage. So it's going to occupy however much space a float takes in memory, and we're allowed to put floats into the value, and that's it. It doesn't have a value yet. We're just saying we're going to need a float, and when you create that space in memory for me, call it percentage, so that when I say percentage, you know I'm talking about that spot in memory. In cases where we have multiple variables of the same type, we want to declare them at once, we can actually do them on the same line like this, separated by a comma, but I personally think this is a little less readable and generally should be avoided. For percentage I and j, these values have undefined. The compiler can't guarantee to us that percentage I or j have a specific value like 0. They could be anything. It's going to have a value of whatever was in that spot in memory before we declared. It could be, usually it's some huge number, either a huge number or a huge negative number. So we need to initialize the variable and give it an initial value. That's called initialization. And we can do that when we declare the variable, as in the case of short x equals 10. So we're creating a new short integer, call it x, give it the initial value of 10. Now I know the initial value is 10. It's a good idea to initialize all your variables in C, usually to something like 0 or -1 or something, just so that you know what the value is. Once a variable has a value, we can assign the value of one variable using another. We can basically treat a variable as being a literal or as being a value because it has a value stored in it. So in this case, we have 3 different variables, and we're using the last variable to initialize the next one. So we create A and we give it a value of 10. Then we create B and give it a value of A, which is 10. Then we create C and give it a value of A plus B plus 5, which is 10 plus 10 plus 5, which is 25. So in this next example here, we're just printing those 3 values. And if I wasn't initializing them first, who knows what values? We get some really awesome values, and maybe even an error because of just the way printf tends to work. But in this case, because it's 10, 10, 25, it's going to print 10, 10, 25, and then a new line. Beyond just making and setting variables, you saw in that last slide, we can also use the typical suspects of math, the addition, subtraction, multiplication, and division, to operate on variables and to operate on literals. Just like normal division in the classroom, please avoid dividing by 0. It probably sounds like a funny thing to say, but it's an easy mistake to make when you're using variables coming into a function. You don't know if it's 0. You would never write a divide by 0, but you might write a divide by b when b is 0, and you might not know b is 0. So this is a simple example of a user-defined function which checks that b is not 0 before trying to divide. And in the case that b is 0, I just return int min, which is from the limits header, as a kind of way of saying there was an error, instead of literally creating a divide by 0 error. Now, for each of the different mathematical operations, there is a special assignment operator. So you can do this. A is equal to a plus 1, meaning set a to 1 more than what it is right now. Or c is equal to c times 2, or set c equal to 2 times what it is now. Instead of writing it this way every single time, there is a simplified syntax like this. So plus equals 1, minus equals 1, times equals 2, divide equals 2. So this is going to do exactly what the things on the left are doing, except without having to have you write the variable twice. And this is especially good for when your variable is 3 or 4 words long, like I'm encouraging you to make them. Now, in the case where we're increasing or decreasing a value by exactly 1, there is another special case, which is the increment and decrement operators. So what this is going to do is it's going to give you the value of a, and at the end of the line, it's going to increase it by 1. So if I print f, a++, and the a is 1 right now, it's going to print 1, And then as of the next line and for the rest of the program, it'll be one more. It'll be 2. If you need the value to increment immediately before the line executes, you can put the plus plus or the minus minus before the variable and it will do it in place, then execute the line of code. Aside from explicitly declaring variables in the middle of a function, there is a special kind of variable found only in functions, which is called a parameter. These are temporary variables which only exist in the function, and they'll disappear when the function is done. We'll talk more about user-defined functions soon, but here is a simple function signature. We'll talk more about user-defined functions soon, but here is a simple function definition. When we call this function, we are required to provide an integer. This is indicated by the int a in parentheses here. Throughout the duration of a function, we can refer to this a and treat it like any other variable. Assignment operators work, but only in the context of the function. The only important thing to remember is that within functions, we can declare variables, but we may also have parameters, which aren't declared during the function, but at the moment that it's called, or at the moment that we define it. When you create a variable matters. If you need a variable to be available for the entire program, you'll want to declare it at the very beginning. If I declare A, then B, then C, I can't reference C in the creation of B, nor can I B in the creation of A. If I declare A, then B, then C, I can't reference C in the creation of B, nor can I B in the creation of A. For instance, this would never work. Depending on your editor of choice, you may see an error like this. So the order of variable declaration matters, but beyond declaration, we also want to keep in mind the order of initialization. For instance, while this may work in the sense that there's no error, all of these variables exist by the time they're referenced, the values are uninitialized. We don't know what's in A when we assign the value of A to B. And because of that, we don't know what value is in B when we assign it to C. At the end, sure, we set A to 10, but we still don't know what's in B and C. And depending on your background, you might think that B and C will now also be 10. But no, B and C are going to be equal to each other, which is some crazy value. We have no idea what. And A is going to be 10. Beyond that, there's also the issue of the scope of a variable, meaning when it's actually going to stop existing, when we're no longer going to be able to access it. And I think that's going to be the most valuable once we've already covered control structures. Control structures is a great chance to cover the rest of the keywords that we talked about earlier. So the first one is the if statement. The if statement, the idea here is that code is only going to be executed if a certain condition is met. So here's a really easy snippet. A is equal to 3. So if A is less than 10, we're going to say, oh, I've seen a bigger A, whatever. It's not the biggest A I've ever seen. That code is going to run. But in this case, if A is 12 and it's got to be less than 10, it's not going to print anything. We're just going to jump to right after the if statement. If we want to invert the meaning of an if statement, we can actually invert the value. So if it's A less than 10, we change that to A greater than or equal to 10. Those are the two possibilities. A is either less than 10, it's equal to 10, or it's greater than 10. We can combine the equal and the greater case, as you see there in that third snippet. So in this case, I've also inverted the meaning of the text. So before it was, I've seen bigger A's, and now it's, damn, that's one big A. And so now we have the two cases covered, but not at the same time. If we use the else keyword, we can cover both cases at the same time. So A is equal to 3. If A is less than 10, we'll say this. Otherwise, we'll say that. And that's what that fourth snippet is doing for us. So this snippet is really an if-else statement. It's not just an if statement, it's an if-else. But the funny thing about the else case is it's not explicitly if and then else. It's if this is true, it's whatever comes after the if statement. And if it's false, it looks for an else statement. And in the else case, it's whatever comes after the else statement. So in this case, I have a block for each. But the truth is that we could actually put another if statement after the else statement, and we can get a little chain going. So if A is less than 10, we'll do this. Otherwise, if A is less than 20, we'll do that. Now what happens in a situation like this where we have if, else if, else if? If I was to take away the else statements, like on the right-hand side, what would change here? On the left, A is equal to 3. So we're going to evaluate A is less than 10. It's true. We're going to do what's in block 1, and then we're going to jump down here to where the orange arrow is. We're going to jump to after the last else statement because we already hit the case we needed, and everything else is just if we fail. But on the right side, A is less than 10. That's true. We complete block 1. But then A is also less than 20, so we do that. And we're going to evaluate this. And when that's done, A is less than 30. And we're going to do that too. So if we have the else keyword between every if statement, that's going to make it so that those cases on the left are mutually exclusive. Only one of them can happen. Whereas if we just have multiple if statements in a row, they can all happen as long as the value is right for it. Because yes, 3 is less than 10, but it's also less than 20 and it's less than 30. So it's going to execute all of those. So if you need them to be mutually exclusive, we're going to want to use that else keyword. Now, in the case where your if statements are using equality, if A is 1, if A is 2, and then for all other cases, something like this is actually a perfect example of a switch statement. So we switch on the value of A. In the case where it's 1, there's our block, and when we're done, we break. In the case where the value is 2, there's our block, and then we break. And then default, which is like our else case, is for every single other value we haven't accounted for, and we like to put that at the bottom, just like how we have to put else at the bottom. It's after we've already considered all the other cases. Now, the switch statement really comes to life with the use of enums, so we're going to talk a lot more about this in a future video when we cover enums. Next is loops. So we'll start with the most common type, which is the for loop. It's the one you've probably heard of even if you've done no programming, and it's generally used if you want to repeat a block of code a specific number of times, though it can be used in many other ways. Here's an example of a for loop expression. This will print the numbers 0, 1, 2, each on their own line. This is great because we don't have to write printf 3 times. We can just write it once and put it in a loop. The general form of a for loop can be broken down like this. First, we set some index value to some starting value. Then we're going to continue the loop as long as I is less than some last value, and that value is exclusive. We're not going to include that value. As we saw in the top snippet, it's going to print 0, 1, 2, and we're not going to print 3 because we have a strict less than sign. If it was less than equal, we would include that case as well. The third piece, the I++, is simply what's going to keep the loop walking forward by one value at a time, and we already talked about the ++ operator earlier. So really, a loop is these 3 parts. There's an initialization, a condition, and a step. The initialization is only going to happen once, before the first iteration when we first encounter the loop. Think of this as happening immediately before the loop instead of as a part of it. Then we have a condition. We always evaluate the condition before we execute the body. This is going to be a Boolean expression. There's a bunch of different conditions you can write for this. The sky's the limit. The idea of using a function instead of checking a value is something that I actually do a lot. You can also just put 1 here and it'll be an infinite loop. Who cares, right? The point is, you're not limited to saying something less than something. And then the step is something that's going to happen every time the loop iterates, every time we finish the body. So usually the step is going to modify the condition. So the step is going to increase a value that's in the comparison of the condition, or the step is going to run a function that's going to modify an entity that's somehow factors into the condition. You need to make sure the step will affect the value of the condition, or you're going to get an infinite loop. If you're checking if I is less than 3 and you're not changing the value of I, then the loop's going to go forever because I will never change. If we didn't have the for keyword, this is how we would write a for loop. We would initialize, and then there's a comment to say, I'm starting the loop here, and we have a condition check. If the condition succeeds, we execute the body, we perform whatever the step operation is, and then we jump back to where the comment is, and we do this indefinitely. Eventually, the condition will fail, and we skip doing the body and step again, and we move on with the code. Let's look at some more examples of a for loop. So this for loop is going to execute exactly 5 times with the values of I 0, 1, 2, 3, 4. Remember, that 5 is a less than, so we're not going to include that one. This is exactly like the first for loop that we looked at, except I changed how many times it's going to iterate. We can also write this loop like this. We can say less than or equal to 4, and it's going to do the same thing, 0, 1, 2, 3, 4, and it won't do 5. Or we could write I is 0, I is not 5. Now, this is probably the wrong one. The last one is probably wrong, because if something in the body causes I to skip 5 and go right to 6, this is going to iterate way more times than we expect, because the number is going to go 6, 7, 8, 9. It's going to go all the way up to whatever the integer limit is. On most systems, it's going to be 2 billion some odd. Then it's going to overflow to negative 2 billion because of the way that numbers are stored in a computer, and it's going to keep adding all the way back up. So instead of getting 5 iterations, we're going to get 5 plus 4.2, almost 4.3 billion iterations. And your program is going to freeze and probably maybe even crash. And also, whatever's happening in your body, maybe you're accessing an array, maybe you're doing some kind of thing that is affecting system resources, you very well could crash the app and maybe even a computer, depending on what your code is doing. Saying not equal to 5, not a great idea in the case that we end up skipping a value. It's better to use less or less equal. Check out this example. This is almost like an infinity case, but again, we're saved by the overflow. So we start at 0. As long as I is less than 5, we keep working. But did you notice something? The step is minus minus. So instead of going up to 5, again, we're going to go down to negative 2 point some odd billion, then underflow back to 2 point some odd billion. And now we're we're no longer less than 5, I guess you could say. And so we're going to stop there. So again, an extra 2 billion some odd loops that we don't want. That's very much not intended. And if we're accessing an array or we're doing something that with a value of I could potentially screw something up and cause some other error, we'll get some other kind of crashes. So be careful when you're authoring your loops. You're not going to break your PC, but you are going to get some weird behavior if you're not paying attention. So the thing about the for loop is you can kind of dismantle it. The initialization, condition, step thing, you can actually omit those individual pieces. So we can move the initialization outside of the loop and it works just as normal. We can take the step portion, which is the third one, and move it down after the body as we see in the second snippet. And like I said before, you can make the condition 1 and make it an infinite loop, and instead move the condition into an if statement after the step and after the body and say if I is the opposite of whatever the condition is, we can break. And that'll quit the loop. So you can really twist and turn the for loop definition, and the for loop can take it. So the for loop is kind of the favorite because of how it has those extra pieces, but you don't need to use them. Now with the while loop, we've basically already covered it by talking about the for loop. Here is a while loop. It looks exactly like the for loop where we pulled the initialization up to the top and moved the step down after the body. So it's pretty much used in the exact same way. A do while loop is pretty much exactly like a while loop, with the minor difference that the body will always execute at least one time. Personally, I'm not a huge fan of the do while loop because usually the condition in the while loop is protecting the body from a case where a value might not be what we expect and something could blow up. So I encourage you to find a place to cram it into your project and share the project with us in the description, a GitHub link or something, because it needs more love, and I admit that. But I couldn't even bother to come up with an example here. Like I said, it's a while loop where the body executes at least one time. Let your imagination run wild. Come up with some reason that this still needs to exist. But we really don't. Now you can write the do and just put true for the while and then do something like we did earlier where you have an if statement and eventually break out of the loop internally. But I think it's better to just use a for loop or a while loop for that kind of thing. Remember how I said parameters only exist within the lifetime of a function? Once we hit this line, the control is reaching the end of the function and we return to the caller. And that means we're going to lose a. Whatever we did to the value in a, which in this case was increase it by 3, will be forgotten once we reach that closing brace. Another way to put this is that the scope of a parameter is limited to its function. The scope of a variable refers to where the variable can be accessed from, where it exists in the code as opposed to where it exists in memory. In the case of the control structures, a variable defined in a given block will only be accessible for the lifetime of that block. Any other blocks defined within that block will also still be able to access that variable. When I say exists here, what I mean is that the compiler will be able to access and assign to the variable with no issue. Notice how after this outer if statement, B is no longer accessible. Also, to speak to the point earlier about the order of declaration mattering, inside the if statement, but before the declaration of B, we also can't access B. Any business we have with B needs to be handled after it's declared, but before it's released. It's as I said earlier, when the block that a variable is declared in is completed or exited, that's when those resources are released. Consider that the main function has a scope of its own, and any variables we declare in the main function will cleanly be removed when we exit the main function when the program ends, which is fine. But if we call a function inside of main, unless those variables inside of main are parameters to that function call, the function's not going to be able to access them. If we need a variable to be accessed from both inside main and inside the other functions, that's when we need to get into the point where we need to use global variables. So a global variable in the context of a single file project is any variables that are declared outside of main. It means it's a variable that all of the functions in the project can reach without needing to use them as parameters and the main function. So here I have important number, which I give an initial value of 10. Function 4 is able to access important number and it uses it to print it to the screen. But also before I call fun4 in main, I make sure to assign a new value to important number. That's not a tremendous example, but a good example would be look at my Raylib, Minesweeper, and Tic-Tac-Toe videos. The two-dimensional array called grid, which manages the cell structure of the game. In the case of Minesweeper, it's like a 10 by 10 or 15 by 15. And in the case of Tic-Tac-Toe, it's just a 3 by 3. That is a global variable because passing around a 2D array is like really frustrating to get right in C, and it's not the kind of thing you want to cover in a video that's supposed to make programming look simple and easy. So I just make it a global variable. It really simplifies the workflow. So lastly, we're on to user-defined functions. So this is probably one of the most important topics. It's the key to writing organized, reusable code. In my demos, I define many user-defined functions, probably at least a dozen for almost every, even simple games, because it makes it easy to organize the code into simple pieces. And when you're dealing with arrays of something, it's nice to have a function that works on one piece of the array, but also to have functions that work on the array as a whole and really compartmentalize that functionality. Even my main gameplay loop is stored in a function called update draw frame. It just makes the main function nice and clean. My main function is only like 20 lines of code, right? It looks really nice. So here's an example of a user-defined function. It's fun5. All it's going to do is return 18 as an expression, which is 7 plus 11, but it's going to return 18. So because it's returning an integer, before fun5, the type of the function is integer, and then I'm making sure the value I return is an integer, which an integer plus an integer is an integer. It's always an integer, so we're good. In main, I set the value of a equal to fun5 and then return it. The problem with C user-defined functions is you need to define the function before you use it. So if we have 20 functions in our project, they all need to come before main, and they need to come before each other. If fun5 calls fun4 and fun4 calls fun3, I've got to define fun3 first, then fun4, then fun5. And having to get a precise order down sometimes makes the code less readable because it makes sense to have one function come after the definition of another for the sake of readability. Furthermore, it's nice to have main be the first function in the project. And so the way that we compat this is we use a sort of declaration of a function, which is called a prototype. So we still need the return type, the identifier, and the parameters of the function, but we don't need the code inside of it. So here is an example, again, a full file, full code example, where we have a prototype, then the definition comes later. So this allows us to basically bunch up all of our function prototypes before main. We can freely use them in main, and we can have the functions calling each other without needing to put the prototypes or the definitions in a specific order. And now we can choose an order for each that suits the needs of, you know, my OCD or what I prefer when I'm writing the code. What is the most readable? Because at the end of the day, and it's kind of been one of the themes of this lesson today, is it doesn't matter how long your function and variable names are. You want to make the code readable so that if you want to go on a break or you want to share the work with somebody else, they can understand what it is you're trying to do, instead of making it overly complicated. The only thing to note about using the prototype system is if you need to change the return type, the name, or the parameters of the function, make sure you change the prototype as well. If those kind of fall out of sync, if they don't have parity, the compiler is going to give some confusing errors. The compiler may not immediately identify, oh, you forgot to change this. And your IDE might not say, oh, you forgot to change this. With that finally marks the end of the video. I mean, I really tried to make this a quick thing. Now, I do encourage you to go to CPP reference and read some of the stuff in the C reference. Read about the keywords, read about the rules about identifiers, read about the entry point to the function. A lot of that stuff is really interesting. Now, if me talking about language specification and language definitions is not that interesting to you, there's still going to be plenty of demos and plenty of project work in Raylib where we're actually making interactive, fun games. And be sure to actually go back to the Raylib website and check out some of the examples And of course, Raylib has bindings to other languages. So if you don't really want to use C, if you decide you want to check out something else, there's bindings to languages that I don't even know what they are. Like it's the first time I've seen the language is looking at Raylib's website. So head on over there and check that stuff out. And be sure to tune back in for when we're going to do some more Raylib demos coming soon.